This video is going to be part 2 of acids and bases in organic chemistry. And the focus of this video is going to be how to predict products in an acid-base reaction, and then how to use both pKa values and the 4 effects to determine which side of the reaction equilibrium will favor. So whether it will favor products or reactants. All right, so to begin, acid-base reactions exist in equilibrium with the conjugate acid and the conjugate base. So if we were to write this out like this, we could use A and B to represent acid and base, and then they would exist in equilibrium. So we would use this we would have arrows going in both directions, and then we have the conjugate base and the conjugate acid that forms. And so here it's important to note that the acid becomes the conjugate base, and the base becomes the conjugate acid. And so in many organic reactions, an acid-base reaction involves the transfer of a proton. And so another way that we could write this is that we have Ha reacting with the base, which form A minus, which is the conjugate base, plus Hb. So you might see this both ways. Different classes will illustrate this reaction different ways, but they're representing the same thing. The key difference is that instead of saying conjugate base, you're drawing in this A minus to represent the A that was the initial acid that is now deprotonated. And the focus is more so on that transfer of that proton or the hydrogen. So to predict the products of an acid-base reaction, the first thing you want to do is identify the acidic proton and the basic lone pair of electrons. And so a few tips for this. In general, positively charged species will act as the acid. So since they're already positively charged, they don't want to pick up another hydrogen. And so some really common functional groups for this are something like NH3. You'll also sometimes see, or some other ones, in OH2 sometimes when it's bonded to something else. Those are probably the most common examples of acids that are positively charged. Negatively charged species often have a lone pair of electrons. And so they'll often act as the base because of that lone pair. And so some examples of that could be in a nitrogen that has 2 lone pairs and a negative charge. Another common example is something like this. Let's say that we have an oxygen with a negative charge that has 3 lone pairs. One of those lone pairs can act as that base. Neutrally charged species are a little bit more difficult to identify because they can act as either, as long as they have hydrogens, obviously. And so sometimes it's usually easier to first identify those positively charged species and the negatively charged species, and then use those to kind of direct what the other one would be. Alternatively, if you have a lone pair of electrons, so either on an oxygen or a nitrogen, you can use those to help identify that those would act as the base. All right, so after you identify the acidic proton and the basic lone pair, you can move on to step 2. And so within the reaction, we will have 2 actual reaction steps. In step 2, we will draw an arrow from the lone pair to the hydrogen. And then in step 3, we'll draw an arrow that breaks the second bond to the hydrogen and give that lone pair that forms from that to the atom that was adjacent to the hydrogen initially. I know it's kind of a lot of words in one sentence, so let's illustrate that as an example here. So in this bottom example, we have 2 separate species. One is negatively charged, so we know that this one has to be the base. And then in the other one, we can see that it's positively charged and has those hydrogens that are available and are acidic. And so in this reaction, we did step 1, we identified the base and the acid. Next, we want to draw an arrow from the lone pair to the hydrogen. So we draw the arrow from the base or the lone pair to the hydrogen right here. So that is step 2 from the steps above. And then in the next step, we want to break that bond of that hydrogen to the nitrogen. So we're going to draw the arrow from this bond between the nitrogen and the hydrogen, and then give that pair of electrons to the nitrogen. And that's because we can't have hydrogen have two bonds. Hydrogen can max have one. So if we're forming a bond to the hydrogen, we also have to break the initial one that was there. And so to draw our products, all we're doing is just redrawing the initial species, but we're just placing that hydrogen on the other reagent now. And what we'll notice is that we started with a negative and a positively charged species and ended up with 2 neutrally charged species. And now we can label our conjugate acid and our conjugate base. All right, and so again, we're all in acid-base reactions that involve a proton transfer. We always have those 2 arrows, one in which we form a bond to the hydrogen and one in which we break the bond to the hydrogen. All right, so that's just the basics of a reaction. The next thing that I want to briefly bring up is just a few tips to avoid some common mistakes. I'll also have a complete video on some common errors that students make when it involves acid-base reactions, but here are some just quick tips for now. So the first is that we want to make sure that we recognize cation and anion pairs. A lot of acid-base chemistry in organic chemistry involves something like a sodium or a lithium or a potassium that serves as a counterion. So these are not involved in the actual reaction. You should never draw arrows for any of these. The only purpose that these atoms serve is to balance out the charge of the organic species in this reaction. So do not draw arrows involving these. Instead, what you want to do is separate out the species into that positive and negatively charged group. So let's say that you see something like this. You're given this reagent. What you want to do is, what I recommend is to just redraw. I'm going to just quickly erase that. So if you see something like this, where you see a sodium next to an organic element, what you immediately want to do is just redraw it as that negative charge and that positive charge on the sodium. And so all of your reaction arrows should involve this oxygen right here and should not touch this sodium. That sodium is just there to balance out the charge. Similarly, some other common examples would involve lithium or potassium. We know that some of those really common, like sodium hydroxide, potassium hydroxide from Gen Chem, could similarly be redrawn like that. And so in this reaction, we want to focus on that OH and then ignore this potassium in the reaction. We still want to draw it in the products, and so I'll have an example of that in a little bit, but we still want to draw it out, but we're not drawing any arrows to the sodium or the potassium. Another really common one is lithium or magnesium bromide reagents, and that involves carbon. So it's a little bit trickier to see since we don't have it, since we omit carbons from our representations in organic chemistry. And so that could look something like this, where we have just a carbon chain or something like that, and then a lithium ion here. And so to redraw that, we would redraw that lithium as lithium plus. And then we would end up with having this negative charge on this carbon. And it's not quite accurate to represent these this way, but for the purpose of acid-base reactions, you can represent these this way to illustrate the electron flow. All right. Okay. The next tip is that acid-base reactions that involve a proton transfer always have two arrows. And so to illustrate this, I'm just going to do the normal HA plus B reaction. And so if we have some acid with a hydrogen that is attached to it and a base, we have a lone pair of electrons that goes to the hydrogen, and then we break this bond right here. So again, in that first step, we're forming a bond. And then in the second step, we are breaking that bond. And so our final product should look something like this, where we end up with A minus, because now that lone pair is on that acid. And then we end up with HB. And here I'm going to highlight the electrons that are involved in this reaction. So this initial green pair of electrons on top of the base that I highlight in green ends up in this double bond, or not in the double bond, in the single bond between the hydrogen and the base. And then for this other bond that I just highlighted in orange, that ends up as that lone pair. And so at every point, you should be able to conserve those electrons and be able to trace where they initially started and where they ended up. All right, so up until now, we've been talking about how to predict the reaction or products in an acid-base reaction. The next part we're going to talk about is how do we determine which side equilibrium will favor. So if we have that acid-base reaction, in the previous section, we talked about how we form that conjugate base and the conjugate acid, and that we use these double arrows to represent equilibrium. So in general, even though things exist in equilibrium, that doesn't necessarily mean that we have 50% of each side. We could have something like this, where let's say the products are heavily favored. Then to show that the products are favored, so more of the system exists in its product form, we would draw that longer arrow going to the right. And so for this one, we have products favored. If instead we favor the reactants, then we would show the longer arrow going the other direction. So we have the shorter arrow going to the right and the longer arrow going to the left. And then if the equilibrium isn't known, so if we don't actually know which side is favored, we could just draw them as equal. Okay. And so to determine which side is favored, we would want to use, we have a few different methods that we could use. And so to determine which side is favored, so either the products or the reactants, we can either use pKa values. So that's option one. Or the 4 effects that we talked about in the previous video. And so for this, we have 2 different ways that we could approach this. Both of these methods should give you the same results. So if pKa values are available to you and you have a pKa chart, you can use that option. If that is not given to you, then you should be able to identify which products are favored, if the products or reactants are favored, based off those 4 effects that we talked about in the previous video. So let's go through how to use both of these methods, and then we'll do some practice problems where we'll go through like how to use both of them and show that we'll get the same result. All right, so if we're using pKa values, we know that the pKa reflects the strength of the acid. And so a lower pKa means stronger acid. So we're going to keep that in mind as we use this method. So in step one of using pKa values, we identify the acid and the conjugate acid of the reaction. So we're going to predict the products and label which one's the acid, which one's the conjugate acid. And then in step two, we're going to determine which one has a lower pKa. So for this, we would generally need a chart or have pKa values memorized. Again, that's not always going to be available to you. There's not a good way to calculate the pKa without experimental data. All right, and then from here, we can use the pKa values to determine which side is favored. So equilibrium will favor the side with the higher pKa value. And I'm going to highlight this just so we always remember that the equilibrium will favor the side with the higher pKa value. And so let's quickly talk about why this is. So for this, let's draw out like a acid base goes to conjugate base plus conjugate acid. So let's say that our pKa value of this acid is around 5. And let's say the pKa of this acid is around 15. So what that means is that if we have a lower pKa, if we have, so if we're looking at this acid right here, if we have the lower pKa, a lower pKa means stronger acid. And so you can imagine if that you're stronger, you want to react. You want to push the equilibrium the other way. And so a lower pKa means that you want to react, means that you want to push the equilibrium the other way. And so if it wants to react, it obviously doesn't want to stay by itself on that side. And so what it wants to do is push the equilibrium towards the products. In comparison to that, if you have the higher pKa, that means that you're weaker. That means you can't push back to push equilibrium the other direction. You are weak, you stay in place. So you don't want to react. So it wants to react less. And that means it is favored. It wants to stay in that form. And so if we were to change these equilibrium arrows to show that, we would show that the equilibrium favors the side with the higher pKa value. And so we would draw a longer arrow going to the right. All right, so that's one way. So for this, again, you would need to know the pKa values. You would have to look up them in a chart or be given them to you. All right, this next method is going to use those 4 effects. And so as a reminder, those 4 effects are the element effect, the inductive effect, resonance, and hybridization. And so given the structures of acids and bases, you should be able to predict which of these effects are going to be relevant based off the structure of the molecules. And so for this, we're going to identify the bases instead. Because remember, these effects give us insight into how stable the bases are. And so instead of identifying the acid and the conjugate acid, we identify the base and the conjugate base. Next, we're going to determine if base or conjugate base is more stable. And I'm going to highlight here, stable is not the same as strength. being more stable means you're weaker. It means that you are happier the way you are. You don't want to react. You want to stay exactly as you are. Oops. So we're going to determine if the base or the conjugate base is more stable based on the 4 effects. So we're going to compare the structures, determine which effects are relevant, and determine if that makes the base or the conjugate base more stable. And then for step 3, we're going to say that equilibrium favors the side with the weaker base. And so if we're a weaker base, that means we want to stay the way that we are. We don't want to react. And what you'll notice is that a weaker base means that it's paired with a stronger acid. And so that's why we end up getting that same result as if we use the pKa values from up here. All right, so let's go through a few examples and see how these two effects end up giving us the same result. So in this first one, we have this nitrogen right here and this OH right here. And so we also notice that we have this sodium. And as I said a little bit earlier in the tips, the first thing we want to do is separate out that sodium to give us, we want to separate it out to give us that negative charge on the nitrogen, the positive charge on that sodium, because that makes it a lot easier for us to follow what's happening. And it'll be easier for us to draw the arrows. And so from here, we see that the nitrogen has a negative charge. So that's going to be our base, which means that the other one's going to be our acid. And in the first step, we draw that arrow to the hydrogen. And then in the second step, we're going to draw the arrow from the oxygen-hydrogen bond to the oxygen. And so if the oxygen-hydrogen bond isn't drawn out, which it usually isn't, you can just kind of make sure that the arrow starts between the two element or atoms and then goes to the oxygen. Or you can draw out the entire bond and show, redraw the molecule to show that electron. But for most classes, this should be fine. All right, from here, all we do is draw out the products now. So we show the transfer of that proton. We end up with a negative charge on the oxygen since that had gained an electron pair. And next, we can label our conjugate acid and conjugate base. All right, so now we have our acids and bases and conjugates labeled. The next thing we have to do is determine the equilibrium. So let's go through the pKa method first. And so for this, we will need to know the pKa values of the acid and the conjugate base. And so step 1 is find pKa values. And so again, you do need a chart for this. There's no way to know these without a chart. And so an alcohol or that OH is around 15 or so. And then the conjugate acid with the NH2 is around 40. And I just got those values from a pKa chart. So next we want to identify, so I'm just going to erase this here. Next, what we want to do is identify which one is higher. And so the conjugate acid has higher pKa than the acid. Since 40 is greater than 50. And so what that means is that the weaker or the higher pKa values are favored. And so equilibrium will favor products. So that because the conjugate acid is weaker, it doesn't want to react as much. It's fine being the way it is. And so based off this method, we got that the equilibrium will favor products. Now let's do the 4 effects method. So for this, we want to identify the base and the conjugate base. And so what we notice is that in the starting material, we have the main difference between these two bases is that in the reactant side, we have a negative charge on a nitrogen. And in the product side, we have a negative charge on an oxygen. And so based off of the element effect, we know that this one is going to be more stable. Because that oxygen is more electronegative than nitrogen, and they're approximately equal size. And so since that is more stable, what that means is that we want to favor the side with the more stable base, which is that conjugate base. And so similar to the pKa value method, the equilibrium will also favor the products. And so we can see that we ended up with the same exact result based off the two methods. And so now we can redraw our equilibrium arrows to show that we're favoring the product side. All right. So let's do this next one here. So here, this one's a little bit trickier. So here, first thing we want to do is identify that we have this lithium here. And so we want to redraw this reagent as having that negative charge and a positive charge on lithium. So we're going to erase that. I'm going to show this negative charge here and that lithium counter ion. And I actually forgot to draw out. We actually also form sodium counter ion here. We just don't really, it's not really important for the acid-base reaction, so it's just the counter ion. All right. So now we know that this is going to be our base. We have that negative charge. It's kind of, we have a lone pair. It's kind of a dead giveaway that's going to act as a base, which means that this is going to act as our acid. And so from here, we don't really immediately see the acidic proton. There's not really a hydrogen that stands out to us. We don't really have a positive charge. And so for here, let's draw out the different hydrogens that exist on this molecule. So we have symmetry, so we know that those hydrogens are going to be equal. We also have these hydrogens here. And then we also have these blue ones here. And so these hydrogens right here, the green ones, are directly next to this functional group right here, this carbon-oxygen double bond. And so whenever you see this type of motif within a structure, you always want to identify those hydrogens as being acidic. And we'll see why in a second. So here, our acid-base reaction is going to go from this lone pair to that hydrogen here. And then we're going to break that bond here and draw an arrow from the carbon-hydrogen bond to the carbon. So now we can draw out our product. And so we end up with that negative charge on that carbon adjacent to the carbon-oxygen double bond. And then we formed a new bond to this terminal carbon right here. And then we have our lithium counter charge. And so here we have our conjugate base is right here. Our conjugate acid is right here. And so now we have formed our products. And so going back to what I was saying a little bit earlier about why that green hydrogen is so acidic, it's because this is resonance stabilized right here with that carbonyl. And so again, whenever you see this functional group, you should be thinking about the hydrogens on the end as being acidic here because it's resonance stabilized. All right, so from here, let's do the two different methods to determine which side will be favored. So for the pKa values, I will write out the pKa values for the acid in the base. So this one is going to be around 20. And then this conjugate acid one is over 50. So very, very high, very not acidic at all. All right. So in this one, we can see that the conjugate acid has higher pKa than the acid. And so what that means is that we will favor the side with the higher pKa. So products will be favored. All right. If we're not given the pKa's, we can also use the 4 effects to determine which side is favored. And so here we want to compare the bases. So in the for both of these, it's both of them have a carbon that has a negative charge on it. However, we have resonance stabilization for the conjugate base. And so the effect that we care about is that resonance stabilization. And so that means that the conjugate base is more stable. It's happier to exist as by itself and doesn't want to react as much as the base does. And so that means products are favored. And so again, similar to that previous one, we end up getting the same result for the 2 different methods. And so if we were to redraw the equilibrium arrows, we would show a longer arrow going to the right and a shorter arrow going to the left. All right, so I'm going to post a video about some common errors with acids and bases. And then if you haven't already done so, you can take a look at this acids and bases practice problems, which kind of go through how to use equilibrium and like pKa values to determine which side of an acid-base reaction is favored.